Welcome to this tutorial of the Slagrunner in ANSYS. We will start by creating a project and starting a Fluent setup by dragging the Fluid Flow option into the workspace. We'll then make sure to save this project. As Slagrunner example. We will then start by creating the geometry using the space claim application. So we double click geometry to start space claim. So now that we are in space claim, we will start by selecting the plan view. So we get just the plane, and then we will start by sketching the outline of the geometry. So we will choose the circle option, select the center, and just drag it out and select a diameter of 400 millimeters. We will then create another circle with a diameter of 500 millimeters. By pressing space, we can select the numbered square and enter any number we want. We will then also create some lines to limit our geometry. So once again, start at the center and draw it all the way out to the outer circle. And we do this for 2 directions, and then upwards we draw a line of 200 millimeters up until the circle. We will then draw tangent lines from here up 200 millimeters. You can always press escape to stop any line that you have started drawing. And then we will just combine these top lines to form a whole geometry. And by pressing escape, we can remove the tool. So now we have the basic outline of our geometry, but we still need to remove some of the excess lines. So we will choose the Trim Away tool, where we can just click the line segments which we do not want in our final geometry. Like so. So what we have done here is create a sketch in 2D of our geometry, but we are using an axis symmetric condition, so we will only draw half of the geometry. We will then use the Pull tool to transfer this 2D surface into 3D. Using the Pull tool, we can select the surface and drag it out into 3 dimensions. When we do this, it is very important to select the No Merge option if we want to keep these different volumes separate. So once again, we will set a length here for the bottom of the fluid for 1000 millimeters. And we will do the same for all the other areas as well. Once again, pressing space to select the number box. To manipulate the geometry in 3D, we can hold the scroll wheel and spin it around if you want to see it from a different angle. Or we can hold the scroll wheel and the control button at the same time, and we can pan around ins basically. So this is the basic geometry which we'll be working with, but we also want to add a small inlet spout. So we will go back to the 2D drawing, sketch mode. We will then select this plane which we want to draw in, zoom in a bit, and we will draw a small rectangle here, which we will set the dimensions to 50 times 50 millimeters. This is now a 2D sketch, so if we use the pull tool in this area, we can then cut away into the whole geometry to create a small inlet spout. And that is the whole tutorial for the geometry. We make sure to save it. And then we exit SpaceClaim. And lastly, before we leave the geometry, we must also make sure that we have enabled the share topology. This will enable these different zones or different volumes to be linked together when we then do the meshing in the next step. So after we've done this, we save and we exit the application. Welcome to the second part of this tutorial. We will do the meshing of the Slagrunner. So we are back in the workbench and we will double click the meshing editor to enter the meshing tool in Fluent. So in the meshing tool, we will once again see our geometry, which we drew earlier. And here we can spin it by holding the scroll wheel, or pan it by pressing Ctrl and the scroll wheel at the same time. We will start by pressing Mesh here and the Update button to create a basic mesh. Now we see that this mesh is very coarse, and we will probably want a much finer mesh to get an adequate solution to our problem. So to address this, we'll go into the mesh and we'll select the element size. Originally it is set to 5 times 10 to the negative 2, so we'll go ahead and set it to 2e-2, which should make the mesh a lot finer, and press Update. Now we have a fairly fine mesh, or still a pretty coarse mesh, but for this example it will suffice. But we may also want to improve the mesh in some area. So we'll go into the mesh and we will insert a sizing option. The sizing option allows us to choose a certain part, for example a body, this bottom body, as the target for this change, and we will set a different element size for this, for example 1 to the negative 2. And if we update this, we will see that the mesh in this area is much finer than the mesh in the rest of the geometry. But the important part here is that we can see that the mesh is still conformal, meaning that we do not have more than one mesh element connecting to another mesh element. So the next step is then to select the different volumes and name them so Fluent knows what we are working with. So we'll select the body selection tool, select this inner volume and the other inner volume by holding Control. We'll create a named section called Fluid. We'll then do the same thing on these two outer layers. Create a named section called Solid. This way Fluent will recognize these areas as different regions when we start the application. We'll also need to name the different boundary areas, starting here in this inner surface, which is going to be the inlet, and on the other side, which is going to be the outlet. Oops. And also this top area, which is also going to be an outlet, but only for gas. Since we are using a symmetry, we want to select these three surfaces in the symmetry region and name them symmetry. It is also important to name the different regions different names. So we'll change the name of this part to outlet top. And we then also want the isolating region to have a name. We will go ahead and name them different things. Isolation bottom. Isolation top.
So to now create the actual simulation, we have to enter the setup, which will start Fluent. But first we need to edit these settings in the Fluent launcher. We will choose double precision and we'll also choose the serial processing. Clicking OK will start the Fluent application. We will have to specify how this simulation is to be carried out. So here we can once again see our mesh with our specified zones, and we will start in the general part of the setup. We will select a transient solution, and we will also set a gravity, which will be partially in the Z direction, where we'll have a gravitational acceleration of 9.5, and in the Y direction, where it will be 2.5. And this roughly equates to 15 degrees angle. We will then choose what models we are going to use, and we will use the multi-phase model called the volume of fluid, which we will solve implicitly with the implicit body force enabled. And we have two phases. We will then enable also the energy equation, so we can calculate heat transfer. And for viscous model we will choose the K epsilon, realizable with the enhanced wall treatment. These are just what different equations we are going to calculate with. We will leave the rest of the settings off for now, and these can be used later if we want to make an even more advanced simulation. Next we will specify what materials are going to be used. So for the fluids will have air, but we will also have a slag, which we will have to create on our own. So we'll base it off water liquid. So we choose it here in the list and press copy. And then we can just edit this to be more like slag, which we want to use, with a density of 3500, a specific heat of 2000, thermal conductivity of approximately 2, and a viscosity of 0.01. The rest of these are not important for our calculation right now, so we'll press the change create and overwrite the water. We can also edit the settings for air, but these should be fine as a start. Now, since we also have a solid, we will edit this aluminum to be alumina, which is what is used as a refracting material. Which has a slightly higher density and a slightly lower specific heat and a lot lower thermal conductivity of approximately 5, very depending on what type of alumina we choose to use. We'll also import steel into our calculation so that we can use that for a outer layer, but these settings are okay to use. So we'll now close these and move on to the cell zone conditions. These define what types of materials are used in the different domains. So here we will change the operating conditions and specify the operating density to be 1. After we've done this, we can go to Setup Physics and List Show All Phases to enable us to choose which phase will be the primary one. And for ease of the simulation, we will choose the slag as the primary phase, because this is the heavier phase, so this usually makes the simulation more stable. Next up, we will start to define the boundary conditions. For the inlets, we will set it as a mass flow inlet, with a temperature of 1600 Kelvin. And then we have to go into phase and choose the slag. And we can enter how much slag we want to be input into the geometry every second. And I will choose 1.25. And we also have to go into air to make sure that we do not have any air inlets. The interiors are interiors, so those we do not have to set any boundary conditions for. The isolation, bottom and top, will both be defined as walls, but we will set some boundary conditions for those anyways, because they will be transferring heat out of the system. So we'll choose the mixed boundary condition with a heat transfer coefficient of 4000 and a free stream temperature of 300, external radiation temperature 300 Kelvin, and a wall thickness of 0.05 with the material steel. Now what this will do is it will superimpose a thin layer of steel outside the alumina and calculate as if we had water cooling outside that steel. This same procedure we'll do for the isolation top as well. Though here we could set it to a lower value, but now just for continuity we will set it to the same. For the outlet, which is this area, we will choose it to be a pressure outlet, which is correct, and the temperature of what flows in will be 300 degrees. But we will also have to specify here that air should be the only phase which enters. So we set the backflow volume fraction of air at this outlet to 1. And we will do the same at the outlet's top. And we'll also check the temperature of the inflow gas here. Okay, and then for the symmetry, they should be of the type symmetry, both for the fluid and the solid. And all these walls should have the thermal condition coupled, so that they will share the thermal activities from both of their sides. And that should be all for the boundary conditions. Next you can specify what calculation methods should be used, and it is usually more stable by using the coupled pressure velocity coupling and with first order upwind on most of these settings, which will give a faster convergence. But it is possible to get a convergence with other settings, and it will most likely be more accurate. Now if we want to save the results from this simulation which we will perform, we can go into the calculation activities and we can set up a solution data export. We will choose the file type to be CFD post compatible, and for now we will choose all the surfaces and all the quantities, so we save all the data, and we will save this as Slagrunner simulation 1, and we will save every 5 time steps. We will also set to autosave every 5 time steps. Now before we can run the calculation, we have to do an initialization. This prepares the mesh and sets some starting conditions in all of the cells. So for this we will set the temperature to 1600 Kelvin inside of the area. and we will compute from the inlet and set turbulent kinetic energy to 0 and turbulent dissipation rate to 0. And the air volume fraction inside of this volume should be 1 from the start, because we will have no slag from the start. Then we can press initialize. Now if we want, we could also patch in some quantity in any of these cells. What this will do is it will tell the program that perhaps only this area should be 800 degrees or another temperature or filled with slag or any other quantity which we may want. But for now we are going to continue to the simulation. So for the calculation we are using a transient mode, so we'll have to choose a time step, how big of a time step we should take during the simulation, and we should start out with a very small time step, something like 1 times 10 to the negative 4, and we will set it to run for 1000 time steps, which will simulate 0.1 seconds of flow, and we will see how fast this goes. And we can also set the max iterations per time step, which will limit the how long the calculation will try to find an accurate answer. Once we have done this, we can press calculate. And now during the calculation we will get to see the iterations in this area here very soon. And the goal for any numerical simulation is to obtain convergence for all of the equations that we use. So we'll have one line for each equation, and the goal is for each of those lines to get below 1 to the power of negative 3, as this is the So we forgot one important thing for the solution to be able to run, and we need to specify the direction of this inlet flow. So right now it is set to flow in the x component direction, which will be straight into the wall, which is not possible. So we need to change this so it runs in the y component direction. So set this to 0 and the y to 1. And now we will have to initialize the solution again, which we need to do after every time we make a change in the setup. Make sure the air volume fraction is set to 1. And then go to run calculation and attempt to calculate once again. And now hopefully this time we will start calculating the solution.